So in this video, I will try to discuss some more interesting problems that I found out recently on complex analysis, of course. So let's see. So we'll start with the first question. So you all know what's the Little Picard theorem. It says that if you have an entire function uh, that misses say 2 points, at least 2 points, then it has to be a constant. Or in other words, if you have an entire non-constant function, then the image of f can miss at most 1 point. And one of the easy proof you can do it using Hadamard factorization. Uh, so, but yeah, so if f miss say some point a, then this has no zeros. So you can write it as e power some polynomial, right? This is due to Hadamard factorization. And then it's easy because this function is surjective. Because exponential is surjective and the polynomial is again surjective function. That uses fundamental theorem of algebra. So you get this is surjective, so this means this has to hit every point. In particular, if this is non-constant. Otherwise, if misses another point, then it has to be constant. Because in that case, g of z has to be constant and stuff like that. That's easy. So let's see if we can generalize this statement for a bit. So we have here an entire function. So the next possible best case scenario you can think of is a meromorphic function. So you know what's a meromorphic function? It says that it's holomorphic apart from the points where it has some poles. So no essential singularities. So the question is f from C to say we have to include the infinity as well because we are talking about meromorphic function. So this you can think of as the 1 point compactification of the complex plane, which is the two sphere. So this is meromorphic, and f misses 3 points. So 3 points. Then f has to be a constant. See, so this is kind of slight generalization of the little Picard theorem, as you can see, because here we are including infinity in the image, and we are excluding one more point from the image to make sure the function has to be constant. So, and by the way, by infinity, if you just take this identification, it corresponds to say the North Pole, right? This is the usual stereographic prediction. And so this is the first thing. Let's see how we can do it. It's really easy. It's nothing fancy here. So what if uh, infinity is in the image of f? Let's see. Let's first do the easy case. Well, in that case, the question becomes really easy because everything follows from again little Picard theorem. Because if infinity is in the image and say f misses 3 points, so those 3 points have say a, b, c are not in the image, then you can take this function, uh, this, right? So this is entire because f never hits a. This is entire, and the infinity correspond to the g of z to be zero. It's obvious. It's 1 by infinity, and then and g misses 2 points. G misses 1 by b minus a and 1 by c minus. And by the way, all of them are distinct, okay, because we are taking three distinct points. So g misses 2 points. So it follows that g is constant, and hence f is constant. Constant, and this follows that f is constant. Right? This is from the little Picard theorem. That's easy because everything, like if infinity is in the image of f, that means what? If has a pole, right? So in that case, that's easy. Now, what if infinity is not in the image of f? Well, that case is even more easy, I think, because well, then infinity is not in the image. That means if misses the point infinity, or if you take this 1 point compactification, it misses say north pole, and it also misses two additional points which are on the complex plane. Well, in that case, because if never hits infinity, it means what? If f has no poles, but because it's a meromorphic function, the only possible singularities are the poles. So this implies simply that f is entire, right? Because it never hit, it has no poles. So yeah, as simple as that. And again, by star, this relation or the result follows, right? Because f is an entire function, and that misses, apart from infinity, there are also 2 points on the complex plane that f misses. So let's call this point a b. Well, in that case, because it's an entire function, it misses two distinct points. Again, by Little-Picard theorem, it follows. So everything essentially boils down to the Little-Picard theorem, apart from the fact that you have to deal with an additional point. And to include that additional point, namely infinity, you need to include the extra condition that f has to miss at least 3 points. So yeah, that's a nice generalization. And one more pretty easy question that I think this question is in the book of Conway. I'm not sure. Uh, Also, another interesting consequence of this Little Picard theorem is that so suppose uh, you take two entire function. Let me call it this. So this is the integral domain of set of all entire functions on C. It's easy to see it forms an integral domain. So if this is this such that uh, f and g are never zero, and say some power of f plus some power of g is so some constant. Let's take once some non-zero constant. Then what can you say about f and g? So in complex analysis, the easy case is the function has to be constant, right? Whenever some these kind of questions arise, you always uh, somehow forced to think that function has to be constant. So and there are several results to conclude that the function is constant in a basic complex analysis. Like you have Liouville's theorem, and you have all sorts of weird stuff like maximum modulus. So everything that the violates the condition, the function somehow one way or the other has to be constant. So let's see. And the easiest way in our case in this video is to use the Little Picard theorem. And it's to start with, we already have both f and g misses 1 point. So if we can find another point that f and g misses, we'll be done. And that basically is this condition because uh, this, so f power n never hits zero, right? Because f never hits zero. This is just pointwise multiplication. And also f power n never hits one because say if some point this is one, this means g power n is zero, meaning g is zero, but that is not the case here because g also never is nowhere vanishing. So f power n is constant, right? So again by star, f power n is constant. So it means what? So let's say the constant is k. So image of f has to be the uh, nth root of this element, right? That's easy to see. But that set is a discrete set, it's a finite set, right? But because f is an entire function, it has to map entire C to a connected set. You can think of like that. So that means f is constant, right? And also, and similarly, it will force g is constant because g power n is 1 minus some constant, say C. Then it will imply g power n to be 1 minus C power n. And again, because it's a constant term, G is a connected domain, G is map from connected domain, it will force F to be a constant. So both of them are really cool problems and easy, of course, because it just uses Little Picard theorem. And the proof of Little Picard theorem, as I say, using Hadamard factorization is not very difficult because You know the polynomial, if it is non-constant, it has to hit every point at least once. And exponential is also a surjective map from C to C star, right? So this is surjection, and from C to C, G is a surjection, so their composition is so what am I doing? We first go from uh, C to C. Oh, sorry, this should be in this direction. Yeah. So this is again a surjection, and so it means if has to hit every point. In particular, if cannot miss 2 points, it can miss at most 1 point. So yeah. So if you just apply this theorem, these two things follows pretty much easily. So yeah, we can stop now.